Hello and welcome to today's presentation on the xtUML process leveraging legacy. Today's presentation will be given in two parts by two different speakers. My name is Cortland Starrett. I will give the presentation from the beginning, and then at about the midway point I will hand over to Campbell McCausland, who will provide the second half of the presentation. Thanks go to the xtUML.org community for making these presentations possible. Be sure to visit xtUML.org and look for these presentations, recordings of previous versions of these presentations, and the ability to download the test models that we're using in these presentations. This is one part in a series of several lessons that have been taught and shared by various members of the xtUML community, and there's also a channel on YouTube. If you search for xtUML channel, you will find this presentation as well as others in this series, and a growing collection of training materials and information shared by various people from the community. Today we will discuss integrating legacy code with xtUML models. You may hear me say a couple of times that models can call code and code can call models, and we will see how this is done in some detail today. We will face the challenge of recognizing the value of our legacy IP, intellectual property, our source code. We will look at system-level design using components with an eye to reuse and legacy integration. Then, as examples, we will look first at integrating with legacy at the generated code level, and then next look at integration and test at the xtUML model level from very early in the development cycle, and do validation and verification in an interpreted fashion from right within the tool. Today's projects start as a derivative of an existing project or are seeded by existing models. So today's projects are a mixture of new and existing components. Almost no project starts with a complete blank sheet of paper and starts from scratch, and that's actually a good thing. It's a much greater risk to start with nothing, and it increases the probability of success, especially with a new technology, if the project that you're beginning is using modeling to extend existing legacy artifacts. Now, these existing models can be either platform independent or platform specific, and we're going to show integrating with both types of components. We want to emphasize reuse and minimize cost and risk. And this is where the mistake sometimes that people make is they think that because you've moved to a new technology, a new language, that you need to throw everything that you've ever done away and start clean and from scratch. And that's just not the case. You actually reduce cost and risk by taking advantage of components that you already have. Either components that you have built in-house, so components and legacy code that you've written yourself or that your company owns, but then also many projects include components from outside suppliers, things that you've purchased, modules from off the shelf, and these are also very helpful to reduce the cost and the risk. If you can buy it, then buy it. If you've already built it, then use it. and using xtUML, you can integrate with it. Code can call models, models can call code. Now, another interesting challenge that we have to deal with when integrating with legacy is that in a model-driven development flow, the starting point can contain multiple levels of abstraction, especially when integrating with legacy. So you may be building xtUML models at a high level of abstraction while integrating with some handcraft code models that are at the next level of abstraction down, at the the platform specific level, target specific handwritten code modules. But in such a case, reuse is still a way to reduce cost and to reduce risk, and we're going to show how that we can perform that integration here in just a moment. As we build our models and integrate with legacy, there's another point that we want to make sure that we follow, and that is we want to add the levels of detail, the increasing levels of detail as we move down the levels of abstraction, but we want to do it in a way that does not pollute the platform independent level of models, and so we'll use a code generation strategy that allows us to do that. Let's review the 4 stages of the xtUML process, and I'll briefly point you to some previous presentations in this series that take you through these 4 steps in a little bit more detail. And so we'll just use one slide to review those for the moment to establish some context. In the 4 stages of the xtUML process, in the first stage, the system engineer is involved in collecting the requirements and providing a subject matter split, basically functional allocation into various components, and then defining interfaces between those components. Now, this work often involves documentation style diagrams such as use cases, sequence diagrams, activity diagrams, communication diagrams, and the like. But the output deliverable into the next stage of the process are the component diagrams and the interfaces between those component diagrams. These then are delivered to the component engineer, the component designer, and often there are multiple components in the top level system diagram, and individual components will then be allocated not only to design engineers but possible design teams, and possibly those design teams are building models that will ultimately be implemented in different technologies, such as embedded C code for one component, VHDL AMS for another component, maybe System C for another component. This system level model can be broken down and allocated by team and by technology. But in any case, the internal behavior of these components needs to be defined, and that is defined by the component designers. And they will express the behavior of the internals of these components using class diagrams, state machines, and action language, which can all be executed and verified at the platform independent level. Testing can then begin actually right from the start. Even the systems engineer can execute the component diagrams and move messages back and forth across the interfaces to vet that out, and we've shown that in previous presentations, and you'll get a hint of that in today's demo as well. But the test engineer is able to execute the design and provide some validation and verification by running the model. Whether we're writing in the lowest level code or some high level modeling language, the way that we know our system does what we want is that we run it. And we can even build test benches that will stimulate it and check for the response, but we like to run it. And so that is one of the powers of executable UML, is that even at the high level, platform independent level of abstraction, we're able to run it, test it, verify it. So we involve our test engineers or systems and component engineers acting as test engineers, running those models from early in the process. We then translate the platform independent models into platform specific models using code generation and tools called a model compiler. This allows us to translate from the platform independent high level of abstraction into the platform specific level, which will include many more details, design level details required by the target, the specifics of the implementation language, the tasking, threading that may be involved, the clocking and time sequencing that may be required. All of these details can be built into the model compiler that will translate the application level model into the platform specific model. In system level engineering, we organize our systems around components. Components define the boundaries between blocks of functionality. Components organize. They contain functional behavior. They restrict data visibility. They are the fundamental unit of execution and concurrency many times in systems, and they serve very nicely as the primary reuse mechanism. Components are black boxes with interfaces. They represent a unit of functionality and execution that has a boundary drawn around it through which the outside world cannot see except through the carefully chosen set of published interfaces. Now, what's nice about this idea of black box with interfaces, or as UML calls it, a component, or SysML calls it a block, System C calls it a module. The same idea lives in many areas, but black boxes with interfaces serve as a common denominator for grouping functionality even across different technology boundaries. Digital hardware can be grouped into a black box exposing interfaces such that the outside world communicates with the internal functionality through these interfaces. Analog hardware, the same way, and embedded code can be broken into components with interfaces that communicate with either the hardware or other software modules. And the same with software in enterprise systems. All systems can break down into these black boxes with interfaces, and that's why using the component diagram or components to organize our system is so useful. These components then can be used as the mechanism for reuse. And in the case that we're going to be talking about today, components define the interfaces between our newly modeled functionality and the legacy functionality that we want to leverage and carry forward in our new design. Now, components are very flexible, and we can actually use components to extend legacy components and package them in a component at a higher level. So components can contain hierarchies of subcomponents, and these subcomponents could be a mix of newly modeled functionality and existing legacy interface. So we're able to allocate new behavior to separate subcomponents. Also, components are pluggable. So if we have two components that have compatible interfaces, then we can easily plug one in place of the other, or perhaps have multiple versions of the same component, one for deployment, one for test, one for behavioral modeling. This idea of the compatibility between components makes for flexible design time decisions. Let's move toward our case study now, the runner's GPS watch. I'm a runner, and when I run, I wear a Garmin that I've had for 5 or 6 years. And this watch, when I step outside, I put the watch on my wrist and turn it on, and it syncs up with the satellites. I mean, it's a little strange to think that a watch that you're wearing on your wrist is actually communicating with satellites that are in geosynchronous orbit over the equator of the Earth. But it does, and it then is able to calculate and record my latitude, longitude, and elevation at any point on the surface of the globe. And the watch then can display in various modes and show me the distance that I've run, how much time I've been running. Sometimes I also wear a strap around my chest that is able to sense the electrical impulses that drive the beating of my heart, so that it can collect heart rate, average heart rate, etc. Then when I get back home from my run, I'm able to download this data from the watch onto my PC and then present a track. And on this is a run in a park in Wilsonville, Oregon, and the red line there is a track of all the GPS points during this particular run. So taking our runner's watch through the four-stage xtUML process, we first break down the functionality into its functional allocation into components with interfaces in between. And we've broken this particular design into a location component, a user interface, a heart rate monitor, and tracking, where tracking is the central component that is collecting the information and accumulating it. Each component is autonomous, it's service-oriented. The focus at this level of system design is on allocation and communication, so functional allocation and then the communication between those functional blocks. We get explicit about the interfaces between the components using an interface definition diagram, and here we try to enforce loose coupling by having a minimal message exchange between the components. The interfaces can be organized into services request, which with each of the messages or all of the messages that go back and forth in a particular interface being defined, including the direction. And interfaces allow a collection of messages going in both directions between the components. Then the components are passed to the component design teams, which take those components and then define the internal behavior for each component using class diagrams to capture the data perspective of the internal behavior, and then using state machines to capture the control, the sequencing of the activities, and then those activities themselves are specified using action language, which is a platform independent processing language, which then can be run to validate the behavior and then later on translated to the next level of abstraction, translated into C or VHDL or System C or whatever the technologies that you're using in your particular system. Let me briefly burrow down into one of the components before we look at this in the BridgePoint tool. We'll look at the tracking component. Inside the tracking component, we have a class diagram that is used to keep track of the route. The route was that red line that we saw on the GPS track, and the route is here called a track log, and it is composed of a sequence of track points linked together with one track point having latitude, longitude, the speed, a timestamp, linked in a sequence, and then with each track log also having a collection of heart rate samples that were collected during that track and sequenced together with the track log. Here we have a state machine, a state transition diagram that shows the runner's watch changing display modes. So we can have the watch display the distance. We can push a button on the display or on the user interface and cause us to start displaying the speed or the pace or the heart rate or the lap count. So there are 5 different modes, and this state machine shows what happens each time the mode button is pressed on the watch and how we switch display modes. Next, we switch to BridgePoint to look at the GPS watch application as it looks in the actual BridgePoint xtUML tool. And we start here with the library package containing the components that have been broken down into the 4 that we mentioned in the slides. We have the location component, which will talk to the GPS satellites. We have a user interface component that represents the buttons and the display, heart rate monitor component, and tracking component, the central component that controls the overall system. In fact, let's look at that packaged in a system format with all the components connected together, and we have now wired them across interfaces so that the tracking is in the middle here, communicating across the location provider and location util interfaces with the location component, communicating across an interface to the heart rate monitor and another interface to the GPS watch user interface. If we drill down inside of the tracking component, we'll see that there's a package inside containing the class diagram that we saw before, where we have our track log collecting and accumulating a sequenced group of instances of the track point data, and then in here is a state machine to show the display, which we saw before, showing the different modes of the display. And then we will also look at the workout timer state machine as we execute this model here in a moment. So for the model-based test, if I look at the system package, we've built a test case that takes the internal behavior of the user interface and drives messages across, basically button pushes that begin the GPS watch running. And I have a test case that will run it through 4 cycles of starting the watch and then pausing it. So I can switch to the debug mode, start up the test, and watch the instances of track point accumulating here as the watch goes from paused to running. And I can even put a spotlight on so that I can see that I'm now running. Okay, I'm taking a rest, I'm paused. I push the start stop button again so that I start running, accumulating track points, and until the to the end of the 4th cycle. we certainly are showing an accelerated version of the process here, where since we're working with a model that is already complete. But let's push that a little further, and now that we have run the model verifier and tested this system, let's switch over to the C++ perspective and generate C code for this application. And even though we have only behavioral test definition for the internals of the UI, it still is functional and it drives messages across the interface. So let's see if we can run the same test case in the generated code. So we'll build the system, including our test version of the UI component, generate the code for it, compile it, and now let's run it. And what we should expect to see would be exactly the same thing that we see when we run in the model verifier, or at least something that looks similar. And so we're running our 4 sequences of pause. You can see we're paused right now, and we just kind of hit the run button again. And in the console here, we're getting trace from the generated C code that is very similar to the trace that we see in the console when we're running in the model verifier. So this takes this full cycle of building the model, testing it in the verifier, using a behavioral stub for the user interface component, and now translating into C code, compiling it, running it, and seeing that we get the same behavior there. Coming back to the slides for a moment, let's talk about real-world component design before we do an actual example of integrating legacy C code with the GPS watch design. Components come from many sources. During the series, we've talked about xtUML and modeling your system, running the system, generating code for the system. And so these components from what we're learning in this series is one source of where we can get components to build an entire system. But we may not want to model all of the components in the system. There may be some that we are more comfortable or have other reasons that we want to build the component at the implementation level, and so we'll handcraft the components. Maybe we've already started, or we're getting a component from another team that is writing the code by hand, and that's great. We can integrate with those types of components as well. And in fact, we may have some existing legacy, or we like to call them realized components that already exist, that we've purchased or that come from a previous design, and we want to integrate those into the system as well. So with our model-driven development flow, xtUML is flexible. Models can call code, code can call the models, we can integrate them together. Now, as we've seen, we will go ahead and build the component diagram for the entire system, both the realized or handcraft components as well as the ones that we are modeling. And then when it comes time to building the internal behavior for those, that's where we decide what to do with execution, integration, test using these legacy components. Okay, back in BridgePoint, we look at the system package for, or the system package for the GPS watch application, and so far I showed that we had behavioral models in here that just simply sent messages across here. Well, it so happens that I have a handcraft version of this UI that communicates to a GUI version of the watch that runs on the system. So I don't want to generate code for this. I simply want to handcraft, stitch in some existing code that I have. So if I look at the generated code provided by the BridgePoint tool, the naming of the files matches, there's a mapping to the artifacts in the models, and here is the UI.c file that was generated. And so what I can do is I can copy this generated file into this other folder, the gen folder, and take advantage of the interfaces that were generated onto this component, and then simply edit in my own implementation. And so what I have done is I have taken that generated shell of a component and edited in calls to some additional handcraft code that I have in this file called GUI bridge. And so all of my calls to GUI bridge then are edited into this shell of a component supplied by the generated code, and I can stitch in my own handcrafted C code. And any files that are found in this gen folder, as the application gets built, these files get copied into the source folder, this folder here, before the compilation and linking occurs. So my handcraft code can override any of the generated files that have the same name. So once I have edited my handcraft C code and put it into that gen folder, I can rebuild the application, compile it all together, and hopefully the compiled version will now invoke my pre-built user interface code. So I will start up my user interface, and my handcraft code simply edited in some socket communication to this module. So if I now execute the combined generated C code and legacy code and generated code, I now have a very nice user interface that I've integrated in that allows me to stop or pause, start up again. Just like we saw in the test case, I can stop and pause and take a rest and then continue going, and then when finally I stop and hit the reset button, it resets my application to the beginning. So this shows how we have simply edited some C code and included it into the build with the generated code, and like I said, code can call models, models can call code. This example demonstrates integrating the components at the generated code level, at the target level, the C code in this case. But it's also possible to integrate legacy code and run it at the modeling level in the model verifier, and that is the next thing that we want to look at, and Campbell McCausland is going to present exactly how that is done and the advantages to doing that. So now I pass things over to Campbell.
We have seen how we can integrate legacy artifacts into the generated code. But we can also treat legacy code as an implemented component. We use the term realized component to mean a component that has been implemented in some design flow other than xtUML. There are many reasons why an alternate flow might have been used, but a common case is where some part of the system is already implemented and is being reused from a previous project. In many development processes, this legacy code could not even begin to be integrated until the implementation phase. This introduces risk to a project because problems such as requirements and functional impedance mismatches only become apparent very late in the project. It can also take a very long time to find and fix defects because there is, by this time in the project, a very large amount of code to sift through. xtUML embraces this challenge by accommodating realized components into the workflow early. As we have seen in an earlier episode, the benefit of using the BridgePoint verifier is that it allows us to begin testing much earlier than with traditional development processes. What if we want to include some legacy code in the test mix? What if we are planning to reuse some legacy artifacts? Can we still use Verifier meaningfully? Verifier offers an external code interface that allows us to do just that. Verifier's external code interface allows messages to be sent to user-provided Java code and allows user Java code to call into a Verifier running model. When combined with Java's ability to integrate with compiled legacy code via the Java Native Access or Java Native Interface libraries, exchange of control and data with arbitrary legacy code functionality is enabled. Let's see how this works in more detail. First, we identify the components we are going to treat as realized. This is usually obvious, since we know at the start of the project what the reuse policy is going to be. Next, we create Java interface definitions for every interface exposed by each of the identified components. Then, using these interface declarations, a realized Java class can be created that implements the component's behavior. This class can be thought of as a glue layer between the xtUML and the realized artifact to be reused. For very large interfaces, the creation of this Java can be automated based on machine-readable interface definition languages. Once the Java layer is complete, we mark the component as realized inside the xtUML model and run Verifier. Any component in a configuration may be specified as being realized in Java. This is set in the Properties view when a component is selected. By turning the realized component property off, you may return to the modeled behavior for the component at any time. In our case study, we are going to provide a realized implementation for the UI component so that we can provide a human-in-the-loop simulation of a real sports watch. Once specified as realized, Verifier expects to find Java classes for the component and for each of the component's interfaces. The required Java code is designed to be easy to write and to relate to the parts of the xtUML model it implements. Let us see now what this Java code looks like. Java interfaces are unidirectional. All the methods represent transfer of control in the same direction, that is, incoming to the implementing class. By contrast, in episode 5 we learned that xtUML interfaces are bidirectional. For this reason, Verifier expects to find 2 Java interface declarations for each xtUML interface. One Java interface defines methods that are directed to the providing component, called toProvider, and one Java interface defines methods that are directed to the requiring component, called fromProvider. This is the only major difference between the structure of the Java source and the structure of the xtUML model. Everything else, from the naming conventions to the package structure, follows the xtUML model exactly. In our case study example, it so happens that all the signals are going from the provider to the requiring component, and all the interface operations are going to the provider from the requiring component. In another example, the signals and operations might have mixed direction. Here are the two Java interface declarations expected by Verifier for the example xtUML interface called Actions and Data. In our example, the UI component is a provider of the Actions and Data interface. The Realize component does logically the same. The Realize component shows that it is ready to handle the incoming messages of the interface by implementing the iActions and Data toProvider Java interface as shown in red. The compiler will then check that the correct methods are actually written for the Realize component. When a message is sent to a Realize component, Verifier will marshal the data and invoke the appropriate method on the supplied Java class. For outgoing messages, we use a Java representation of the xtUML port. This appears as a Java instance of something that implements the FromProvider interface. The builder of the realized component does not need to implement this instance beyond seeing to it that the Java interface is declared. Verifier dynamically creates the implementation of this port instance at simulation startup and passes it to the constructor of the supplied Java component. Once the Java realization of the port is cached within the realized component, making outgoing calls is easy. We simply call the required method on the port instance. Marshalling the passed data and transferring control into the model is all taken care of by Verifier within the supplied port implementation instance. In our case study project, we have a requirement to reuse a graphical simulation of our sports watch. This simulation was coded in Java for a previous project. This makes it a good fit to integrate into Verifier using the interface to realized code. So here is the GPS watch model once again. Let's reset to the stage where we have only modeled functionality. Although we could create a model for the UI component, let's say we are planning to reuse that existing graphical simulation that was created during the proof of concept stage of the GPS watch project. As a result, we have not done any work on the UI component beyond creating a model test stub. We can simulate the tracking component by manually executing messages wired to it. But that's really about it. Here is the graphical simulation, but we can't connect to it because to do that we need to call Java methods. Now let's switch to the Java perspective. Here is the Java created to implement the Actions and Data interface. Note that the classes are found following the same package hierarchy as was already specified in the xtUML model. Here is the FromProvider interface declaration. And here is the toProvider interface declaration. Finally, here is the implementation of the UI component. The implementation of the init message creates an instance of a handwritten class called GUI connection. When this class is instantiated, it starts a Java thread that listens for button press notifications on a socket. It also handles requests to update the graphical watch display. There are a couple of things to note about this class. Firstly, it obeys the same naming and packaging rules as we saw for the interface declarations. For example, the class name UI matches the name given to the xtUML component. Notice that the constructor takes the same form as was introduced a few minutes ago when describing the implementation of the from provider interface. Finally, note that the UI Java class implementation is a superset of the interfaces expected by Verifier. For example, there is nothing in the xtUML model specifying the existence of the GUI connection class. This superset capability allows a lot of flexibility in providing realized component implementations. Switching back to the xtUML perspective, we can check that our realized component covers everything we need to implement the UI component. First, we mark the UI component as realized. Now, when we right-click on the component in Model Explorer, we see a new menu item, Audit Realized Bindings. Choosing this shows us a report that tells us all is well. If I add an argument to the setTime interface operation, the audit report will tell me that I have work to do in the realized Java. Now we'll just remove that. And now, when we run this model in Verifier, the messages sent to the UI component are executed by our Java realization, and our graphical watch exchanges data and button events with the running Verifier model. So, to sum up, the xtUML process is flexible in its approach to legacy code. Legacy artifacts may be integrated during Verifier model simulation and with the model compiler output. The component approach that xtUML embraces enables and supports this mixed source approach. Modeling components in xtUML is the recommended route for a project to follow, but where necessary, legacy code may be integrated by representing them as realized components. We can validate modeled and reused functionality together by co-simulating. When this is done early in the project, risk is minimized. Finally, through the ability to integrate legacy code into the model-driven development process, a complete approach is supported, even when reuse of legacy code is required. Cort and myself would like to thank you for attending our seminar today. Although we have covered a lot of ground, in truth we have just scratched the surface of what you can do to integrate legacy code. Please check often at xtUML.org, as we are hoping to produce further episodes to expand on this topic.